As promised, we are going to write the game of life. And before I dive into the code, let me describe what this game is, what the rules are, and get us thinking about how we are going to design the data structures and how we are going to design what algorithms we need, what classes we need, and that's where all the hard work really is, and then of course we'll go ahead and implement everything. So the game of life simulates a bunch of biological cells that live in a colony. This is, for example, a colony here. The colony is a two-dimensional, so rows and columns, grid. Each cell is a square in the grid. So this is the entire colony that you see here. Each little square that you see here is a cell. It cannot move. They are stationary, they are locked in, but they can change behaviors as you will see. Every cell is either alive or dead. There's only two states in this colony. So living cells are blue, so all the cells that you see here are alive, and the dead cells are rendered as yellow. Okay? And there's going to be some rules as to how these cells decide whether they live or die or reborn. Okay? And let's go through those now. So in this colony, in the game of life, time moves in discrete steps called generations. In each new generation, so tick, tock, time, a cell can be born, it can just survive, nothing changes, or it may die. So at every iteration or generation, we have to make a decision for each cell. Should you be born if you are obviously dead already? Do you just survive, you're alive and everything is fine? Or you're alive and maybe you are now dead? Okay, so those are three things that can happen. Now, how do we decide that? There's some simple rules to the game of life, and here they are. A cell has 8 neighbors, so pick any cell that's not on the border here, and I'll come back and deal with the border in a few minutes. It has 8 neighbors, left and right, top and bottom, and then the 4 diagonals. Yeah. So a cell has 8 neighbors. The number of living neighbors that a cell has in one generation determines its fate in the next generation. So you are dependent. Your fate depends on your neighbors. Now, here are the rules. If the cell is alive, so it's rendered as blue, and it has 0 or 1 living neighbors, then it dies of exposure and is dead on the next generation. So I'm a cell, I look around me, nobody around me is alive, nobody or only one person's alive, I die of exposure, I don't have enough protection from my neighbors. Okay, rule number 1. Rule number 2, if the cell is alive and has 4 or more living neighbors, it dies from overcrowding. Way too many people around me, and I am now dead. So look at my 8 neighbors, 0 or 1, I die. I'm alive, then I die. If it's 4 or more and I'm alive, then I die as well. Now obviously the game's not interesting if all you can do is die. There must be rules to be reborn. So if the cell is dead and has exactly 3 living neighbors, then it's the sweet spot. You're not overexposed, you're not overcrowded, and you are reborn, and you are alive on the next generation. And if none of those 3 conditions hold, 0 or 1, you're alive, then you die. 4 or more, you're alive, then you die. Exactly 3, dead to alive. And if none of those hold, well then nothing changes. If you're dead, you stay dead, and if you're alive, you stay alive. Okay, so those are the 4 rules, very simple. Nothing very complicated, very easy to define. But let's make sure we understand it by way of a couple of examples. So here's a little, tiny little magnified view of just 8 neighbors of one cell. So that center cell we have to make some decisions for. And its fate, whether it dies, lives, or stays the same, depends on its 8 neighbors. Okay, so let's go through the rules. So if I'm alive, so I'm rendered in blue, and the number of living neighbors is 0 or 1, there's 1 right there in the bottom right-hand corner, then I die. So on the next generation, I'm gone. I haven't made a decision about this guy down here in the corner. I'm only making a decision for that central one right now. Okay, so that was rule number 1. Rule number 2, if I'm alive and the living neighbors is 2 or 3, then there's nothing to do, right? So we're fine. So once you get to 4, then you have to worry about it. So for example, in this case, I have 2 living neighbors. I'm alive, and so everything stays the same. I don't change. Okay, good. Rule number 2. Rule number 3, if I'm alive and the number of living neighbors is greater than 4, here I have 1, 2, 3, and 4, and then on the next iteration, next generation, I'm dead from overcrowding. And the last rule is if I'm dead, I'm rendered in yellow in the center, and exactly 3, any 3, doesn't matter whether these 3 or any other 3 are alive, then I'm reborn on the next generation, and I go from yellow to blue. Good. Simple rules, right? And you can see the conditionals, you can see the check to see how many neighbors you have and all that. Now, how we implement the details of that, we'll see in a little bit when we look at the code. Oh, sorry, one last thing. If I am dead and the number of living neighbors is not 3, well, then nothing happens, right? So here I have 4 living neighbors. I'm dead, but I don't get to be revived because I need exactly 3 to be revived. All right, now the only thing we have to deal with now is the border case. Because if I look at this guy with a little X here, who is its 8 neighbors? I only count 1, 2, 3, 4, 5 on the lattice. And what we're going to do is we're going to wrap around. So imagine taking the colony and turning it into a cylinder. So then these guys over here are its 3 neighbors that would be here. It's a decision we have to make. We have to somehow deal with the fact that you may not have exactly 8 neighbors. And so I'm going to assume wraparound. So these guys on the other side of the colony impact me. Okay, so that deals with everybody in this column right here. Now every point has 8 neighbors. Of course, the same is going to be true up top. So instead of wrapping around vertically, I'm going to wrap around horizontally now. So this guy's 8 neighbors are determined by, at the top, are determined by the 3 neighbors at the bottom. And then the only thing we got to deal with is the corners. So the corners just do all the wraps. So here, I'm going to go up and down. I've got 2 neighbors down here. I've got 2 neighbors over here. And then I've got my last one down in the corner. So we've just got to deal with that wraparound in the corners to make sure we always have 8 neighbors, because there's no other rules. I don't have a rule to say if I'm at the edge, only 3 of my neighbors. I could have done that, but we're just going to do the wraparound to deal with that. All right, now we know the rules of the game of life, and now we've got to just think through a few things. How do we represent the data? What objects do we need? And then how do we implement the various functions? So let me just talk a few minutes before I show you the code on representation, because that's really sort of the magic here. Yeah, because if you do this right, the implementation is going to be pretty easy. And if you do it wrong, it's going to be a mess. And that's, by the way, generally true. So let's think about the colony. Forget about objects and classes for a minute, and let's just think about the colony. What is it? It's a 2-dimensional array of things. What thing is it? Well, a cell, which sounds like it's calling for an object or a class of type cell. So every element in that colony is basically the same thing. I have to be able to do a few things to it. I have to be able to draw it. I have to be able to revive it. I have to be able to kill it. I have to be able to determine how many neighbors it has. There's just some simple things I have to do. And every cell is going to be treated the same, except maybe just how we compute the neighbors on the left, right, and top, bottom. So it does sound like I'm going to have a cell object. But how am I going to represent the colony? Well, that's screaming for a 2-dimensional list. If you think about just a single row of the colony, well, that's a list of objects. And if you think about the 2-dimensional, that's another list. So I'm going to have a list of lists. The first element is the first row. The second element is the second row. The third element is the third row, and so on and so forth. So we're going to build a 2-dimensional list. Every element in that 2-dimensional list is going to be a cell, and every cell is going to have a functionality. All right, so there's the basics. I've got 2 classes, a colony class that is responsible for implementing the rules, a cell class that doesn't know anything about the rules. The cells are just the cells. All they can do is render themselves and either die or live. The colony is going to implement the actual algorithm and the rules for the game. So I've got 2 classes, cell, colony, and I sort of see how I'm going to represent this big colony with a 2-dimensional list of a bunch of objects of type cell. All right, that's the basics. And now what I'm going to do is switch over to Jupyter Notebook, show you the code, show you how I built up the cell class and then the colony class, how I built some drivers to test everything, and then we'll see what happens when we actually run this thing in full animation. So I'll be right back in Jupyter Notebook, and we'll start going through the code. Welcome back. So what I'm going to do now is go through the code for the game of life. Okay. So remember, we're going to have 2 classes, the cell class that's really just responsible for what a single cell does, and then the colony class, which is responsible for implementing all of the rules and regulations for playing the game. So let's start with the cell class. Okay, so first things first, I'm going to define this global variable, which is going to define the size of the cell that will be drawn in a colony. And I've made this a global variable now just to simplify things. So here is my cell class that you see up here. It has a constructor and then 1, 2, 3, 4, 5 functions associated with it. So let's start with the constructor, and then we'll go through the functionality that we wanted to implement on a cell class. So the cell, remember, lives somewhere on a two-dimensional canvas. And eventually we're going to want to draw it. But conceptually, it's really being stored. Remember I said the data structure is going to be which row and which column of this grid are you in. So I'm going to choose to store the representation of the cell using a row and a column as input. So I'm going to say I want a cell in position 1, 1. That's the top left-hand corner. I want a cell in position 1, 2. That's the one over going horizontally. And then as many as there are in the columns, and then many in the row. So the constructor is going to take two numbers. Which row and which column are you in? Now, eventually, I'm going to want to draw these things. So instead of storing just those numbers, I'm actually going to store them as x, y coordinates. And you're going to see in a little bit that that's going to be the most important thing because mainly the cells, all they have to do is draw themselves. So I'm going to store the x, y location as the column times the cell size and the row times the cell size. So let's make sure that makes sense. So, I should have indexed on 0, sorry. So the top left cell is going to be 0, 0. So that will be at position 0, 0 when I convert into pixels. Move over 1, x gets incremented by 1. Column gets incremented by 1. What does x get set to? 20. So the first one's at 0, the next one's at 20, and then the next one's at 40, 60, 80, 100. So by multiplying by 20 times which column I'm in, I'm specifying the pixel location that the cell will be drawn in, and of course the same will be true for the y coordinate. So I'm choosing, because I figured out, this is again of course trial and error, you may not have known this in the beginning, that I really needed the xy coordinates. Now, I could have saved the row and column and the xy, but you'll see later on I don't really need the row and column anywhere down here for the computations, so I'm only going to store the xy. And of course, the only thing I have to know about a cell is it living or dead? Yeah, that's it. And by default, I'm going to set all the cells to dead. So there's going to be a living data parameter, and it will be a Boolean value. It's true if the cell is alive and false if it is dead. Now, I could have passed in a parameter here to specify it. I didn't need that, so I just didn't do that. All right, so that's the constructor. Please store for me where on the colony in pixel location is the cell's location. It's static, of course, it doesn't move. And then store a value living, which by default will be false, but of course we'll be able to change that. Now, I have 4 functions here that allow me to change the state of living of a cell. And let me just go through them, and then I'll tell you why I have 4 different ones. Actually, it's only 3 and then one that tells me what the state is. So let's do these 3 here. So I have a function called kill, which takes a cell and kills it. If it's already dead, I kill it again. And if it's alive, I kill it again. I kill it rather. So how do I do that? I just take the living parameter and I set it to false. So it doesn't matter what it was set before, I set it to false. I have a similar function called revive, which sets living to true. If it was false, it'll go to true. If it was true, it'll stay true. So these are just kill it, revive it. I don't care what the previous state was. The flip is reversing the state. So here I'm going to say self.living equals not, or is assigned rather, of self.living. So what am I doing here? I take the current, if it's living, self.living is true, I set it to false, and that's the new value. If it's false, I set it to true, and that's the new value. So you'll see later on I want to have the ability to do all 3 of these. Kill it, revive it, and then flip its state. Okay? And then, of course, you just know you need to query the state of a cell, because that's what the rules need for me to figure out how many neighbors around me are either dead or alive. And instead of forcing another class to reach in and grab this, I'm simply going to write an accessor function that simply tells me whether a cell is alive or not by simply returning that parameter. Okay, so constructor, 3 functions that can alter the state, live or dead, of a cell, and then a function that returns the state of a cell, which we know we're going to need for the rules, and then finally the drawing. So the drawing, all you have to do is draw a little square at the XY location. And remember again, I'm storing pixel locations here. So I'm going to define a canvas down below. You'll see it in a second. I'm going to draw a rectangle at XY of size, cell size, 20 by 20. And if self.living, then I'll render blue with a black outline. And if it's dead, I'll render it as yellow with a black outline. Notice here that I've actually tapped into its parameter, living. You could make the argument that you can call your own function here. I think it's okay to do this here, particularly in a small class, because it's my data. But probably for consistency, I should have used the isLiving function and called isLiving, and so that way I don't have to worry about if this variable changed, I don't have to worry about changing it anywhere else. In either case, I check the status and I either render it as blue or as yellow. All right, so let's go ahead and evaluate this. And let's evaluate our first. Now, the first thing, before we get to the colony, I've defined a bunch of functions here, and I have to make sure they work. And so this, again, is an exercise in incremental coding. Write a couple functions, test them. Write a couple functions, test them. Before you start doing the hard work of the colony, make sure everything works here. So let's do a couple of tests. I'm going to define a canvas of 400 by 400, so there'll be 20 rows, 20 columns and 20 rows. They're each of size 20. I'm going to define a cell at 0, 0, which in my case is in the lower left-hand corner. So notice here what I've done is I've moved the origin to 0, 0. There's no reason to do this. I just didn't want to deal with negative numbers here. So this is going to be 0, 0, positive in the horizontal direction, positive in the vertical direction as I go right or upward. I'm going to just draw that cell. So at this point, I should be able to see a yellow cell because by default it was dead. I set living to false. And I'm going to print its state to make sure that I can also tap into the variable properly. And I see that C1 is living, returns false, and then I render the canvas. So there's a dead cell in 0, 0. Good. Let's make sure that I can flip the cell's state. So I've called C1, that's the cell that I just created, flip. That should go from false to true, dead to living. Let's draw it. It should be rendered in blue. There it is, same location. And now isLiving returns true, C1.isLiving. Good, so the flip function and the draw function seem to be working. Let's just make sure that I can go back and forth. So if I flip again, then it should go back to dead and rendered in yellow. Okay, good. I feel pretty good about that. Let's define another cell. Let's make sure that our spacing is right. So I'm going to define a cell at 1, 1. So I'm going to move horizontally 1, vertically 1, and it should be in the upper right-hand corner. It should be in the upper corner of the previous cell. I'm going to draw it, and you can see here I've got my cell now, my 2 cells right here. And this one, of course, is also dead, drawn in yellow. Let's test the revive and kill function. So I'm going to revive 2. It's dead, so it should come up as living, and it's living. Good. Let's go ahead and kill that, and now everybody should be back to yellow, and it is. Good. Bare bones testing, you probably want to do a little bit more, so let's just, and make sure that the multiple calls to kill, if it's already dead, it stays dead, and so on and so forth. Now, we know we're eventually going to want to build a colony, so let's see if we can at least build the basics of that before we dive into the class. So what I'm going to do here is I know that I want to render some number of rows and some number of columns. So I've written nested for loops. So for each y, that's going in the vertical direction. For each x in the horizontal direction, I'm going to create a cell at position xy. So here you see, by the way, y passing in xy is really nice because I don't have to worry about pixels here. I don't want to have to worry about that. I just want to know what position I'm in. And once you tell me that the bottom left-hand corner is 0, 0, I know 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5 going up or to the right. So I'm going to build a cell. I'm going to just, for fun, flip a coin here. So I'm going to draw a random variable, random number between 0 and 1. And if it's less than 0.5, half the time, I'm going to revive the cell that I just created, and I'm going to draw it. and then I'm going to render the canvas. Now notice here, I'm not storing these cells. Notice that there's only one variable here called C. I'm not putting this in a two-dimensional lattice, two-dimensional array, two-dimensional list. All I'm doing is drawing it to make sure that my code works. Now, can I run a colony from this? No, I haven't stored anything. So when we go to do the colony class, we're going to have to do a little bit more work. But at this point, I feel pretty good about my cell class. Seems to have the basic functionality. And invariably what's going to happen, by the way, is you're going to write the first class and you're going to realize you forgot to write some functions. That's fine. Just go back and put them in as you start realizing you need some functionality, and understand that these processes are iterative. You have to keep going back and forth. All right, let's do the colony class. Actually, let me just go ahead and run this so you can finally see what this thing looks like. So this is the colony class running, and I'll go through the code in a little bit. So you can see every time the screen flashes, that is a new generation. Some cells stay the same, some cells die, some cells are revived. And every time you play this, there's obviously a stochastic or random component to it, so it'll be a little bit different. Sometimes the colony will get into a steady state very quickly and just lock in, and nobody dies, nobody lives. Sometimes you will wipe out the whole colony very quickly just because of overcrowding. And then sometimes, like in the case, it'll just start to evolve. And what you should see is that it will go from undercrowded to overcrowded. So what will happen is at some point too many cells are alive, lots of people start dying, but then it's just ripe for rejuvenation and they start coming back. And you know, it's very unpredictable what will happen here, but I'm going to go ahead and just stop this so we can now start looking at the code. So you can run this on your own and see what happens over time. And I've just set it to be 100 iterations, so you can set that to be a little bit more. All right, so let's go up to let me show you the driver first, just to show you how simple this is. So, of course, I have an animation. I'm going to set this to just run for 100 times. I'm going to define a canvas. Here's my withdraw animate Jupiter. I've got a draw frame function, and I'm going to call draw frame. So on each iteration of the animation, I call a draw frame, which is this. This calls, Hive is the colony, which is the class I'm about to show you. I compute the generation, so I decide who lives, who dies. We play God in that function, and then we draw the hive, and then we return the canvas, and that's the whole driver. All right, so all the work is being done up in the colony class, and all we have to do is compute the generation, implement those rules for who lives, who dies, draw the colony, and do that over and over and over again, and we get the game of life. So now let's go ahead and look at the colony class. This is it here. It's not too bad. Let me just come up to the very top here. All right, here's my class. I have, of course, a constructor. I have a draw function and a compute generation. So the draw function is just going to call the draw of each cell in the colony using the draw function from the cell class. The hard work is in compute generation. Right? That's the thing where all the rules have to come into place. But let's do the constructor first, and then we'll go into the compute generation function. So if you remember from the previous lecture, I said, how do we represent a colony? Well, this is really screaming for a two-dimensional list. Why? Because I have some number of columns, some number of rows, and stored in each one of those is an object of type cell. So that's what I'm going to do. So the constructor takes as input the number of rows and the number of columns in your colony. And of course, I'm going to store those because I probably need those somewhere down the line. And now what I'm going to store in the constructor is a two-dimensional list where each element is going to be an object of type cell, which means, of course, I have to call the cell constructor. So let's go ahead and do that. So let's initialize cells, another word for colony. I didn't use colony because that was the name of the class. So cells is the entire thing. It's an empty list. And now what I have to do is create a list of lists. Inside each of those elements is a cell. All right, so for row in range rows. So rows tells me how many rows are in the colony. So for each one of those, I'm going to do what? I'm going to take the object, which is the colony, cells, which eventually is going to be the two-dimensional list, and append to it an empty list. So why am I doing that? What did I say a two-dimensional list is? It's a list of lists. So cells is a list, comma delimited stuff. Inside of each one of those elements is another list. So I have to insert a list in there, that's the empty list, and now I'm going to shove things into there. And then when I come back on the next iteration of that loop, I'm going to create another list. That is the next row, and then the next row, and then the next row. All right, so for each column that I'm specifying, I'm now going to shove something into the innermost list. So self, that's the colony object. Cells, that's the two-dimensional list. Which row do you have? That's the one we're on right now. Append to that inner list. So notice that this is an element of the two-dimensional list. Append to it a cell, a call to the constructor at position, row, column. Good, so now, and then what I'm going to do is I'm going to decide whether I want that cell to be alive or dead the way I did in the previous code. So I'm going to flip a coin, uniform number between 0 and 1. If it's less than 0.5, I'm going to flip that state. So I'm going to make it from false to true or true to false. Now, I could have just said revive this, but I chose to use the flip function. So again, the object colony, the two-dimensional array called cells, tap into row, column. That is now an object of type cell and called the flip function associated with it. All right, so at the end of this constructor, the colony class has three things. The number of rows in the columns in the colony, we're always going to need those, and then a two-dimensional list, each element of which is a cell, which half of which will be alive, half of which will be dead. Good. The drawing should be pretty easy, so let's go ahead and do that, and then we'll do the hard work of compute generation. All right, so let's look at the draw function here. So the draw function, of course, doesn't take any input, and all it has to do is draw every cell. Well, how do I draw a cell? Well, the cell class told me how. So all I'm going to do here is for each row and for each column in self.rows, self.columns, that's what I just initialized up top in the constructor, I'm going to reach into the object, reach into the two-dimensional list, reach into row, row, column, column. That is what? An object of type cell, and call its draw function. So here you really see the power of these abstractions, right? The drawing of colony is trivial. Once every cell knows how to draw itself, I just have to tell every cell in my representation, please draw yourself, and then the magic happens. Everybody does their job. So the draw function is pretty straightforward. All right. Now the compute generation is where all the magic is. So that's this little bit of code right here, and it's actually not too bad. It's all on the screen right now. Okay, so let's do it. Let's think through the logic here. So in order to determine if a cell should be born or die, I need to know how many people around me are alive or dead, right? That's all the rules are determined by that. So this code has two main components. It has this part right here, which is computing the number of living neighbors for each cell, and it then has the implementation of the rules based on 0 or 1, 4 or more, or exactly 3 living neighbors, and that's the logic there. So let's do the top part first. So first thing what I want to do, so one of the tricks with these generations is I have to decide for every cell whether it lives or dies, yeah, or whether it's revived or killed. Now, I can't, however, start changing each cell from bottom to top or top to bottom before I figure out who all the living neighbors are, because then I'm mixing generations. So I have to sort of take a snapshot of where I am, look at whether everybody is alive or dead, and then make decisions for everybody en masse. So I can't start killing and reviving people at the bottom of the colony, because then I change what impact it has on everybody else. So the way I'm going to deal with that is I'm going to go through the whole colony that is now static, it's locked in. I'm going to figure out how many living neighbors do I have, and then I'm going to implement the rules. So let's go ahead and do that. So to figure out how many living neighbors I have, I'm going to build another two-dimensional list, and in each cell, it's going to tell me, for that cell, how many living neighbors do you have? Okay, so let's do that. So let's create an empty list called living neighbors. For each row in self.rows, that tells me how many rows are in the colony, I'm going to append a list of zeros. And this is a little cute little shorthand for creating a list of zeros of length columns. So living neighbors is the two-dimensional list. It has a number of elements in it, a list, a list, a list, a list. There are rows, elements in the list, and then in each element of that, I have a list with columns in it. In this case, it's all 20 by 20. So this little shorthand says to please create a list for me of zeros of this size, 0 times self.com. It's a little shorthand. I could have just written another for loop that did a bunch of appends of zeros as well, the way I did up top with the initializing the cells of the constructor. All right, so at this point what I have is living neighbors is a two-dimensional list, 20 by 20 in this example, with a 0 in every place. And now my job is to go through that, and for every element for that cell at some position XY, figure out how many living neighbors there are, and then fill it in right there. Okay, so let's see how I'm going to do that. So of course I've got to go through every single element in the cell. So for row and self.rows, for column and self.columns, so we're going to go row, bottom to top, left to right, and I'm going to say if I am alive, so I'm reaching into the object, I'm reaching into the two-dimensional list called cells. I'm reaching into element, row, column, and that is a cell. And I'm going to ask, are you alive, by calling the isLivingCell function. So if I'm alive, that means that all of my 8 neighbors has at least one live neighbor. Yeah. So you can think about this calculation in 2 ways. I could sit in a cell and I could ask how many neighbors around me are alive. Or what I can say is, if I'm alive, I affect 8 people, so I'm just reversing that calculation. So if I'm alive, I'm going to tell all of my 8 neighbors in living neighbors to increment by 1. Why? Well, because I neighbor them and I'm affecting their livelihood when we go to implement the rules. All right, now all I've got to figure out is who are my 8 neighbors. Now, if we didn't have an edge boundary, that would be really easy. So if I'm in position row column, to my left is column -1, to my right is column +1. Above me is row +1, and below me is row -1, but we've got to deal with the wraparound. So if I go from 0 leftward, I've got to go all the way to the very end. And if I'm at the top and go up, I've got to go to the bottom, and vice versa. So if I'm at the right, I wrap around to the left. If I'm at the bottom, I wrap around to the top. And that turns out to be super easy to do with the modular operator. So row above is row -1. That's what you see right here. And row below is row +1. Remember, we've put the origin at the bottom left-hand corner. Similarly, the column to my left is column -1, and the column to my right is column +1. So that will work just fine for the inner boundary of the colony, but for the edges, I need to modular divide by rows and columns, and that will deal with the wraparound, so I can never go below 0. I can never go beyond the total number of rows. So by simply doing these modular divisions, I get the wraparound for free, and we've of course seen that before. Now, once I know row above, row below, column left, column right, I know my 8 neighbors by just combining them. So, for example, here I'm going to take living neighbors of row above, column left, add 1 to it. Row above and column, that's the guy right above me, add 1. Row above, column right, that's this one here, and so on and so forth. So I go doop, and then to my left, to my right, and then the row below me. And notice in each of these cases, all I'm saying is everybody who touches me I've incremented their number of living neighbors by 1 because I'm alive. Yep. Now, notice that when you get out of this doubly nested for loop, I've built a new two-dimensional list. And every single cell in there now knows how many live neighbors they have, and now I can implement the rules. So let's just go ahead and implement the rules. All right. So what do I do now? So I've measured the number of living neighbors, and now I don't care what order I kill or die, because we're going to do that in one sweep, and then we're going to go back and compute the generation all over again. So for each row, for each column, nested for loops, of course, and now I've got some simple rules. If the number of living neighbors at position row column is less than or equal to 1, or greater than or equal to 4, then just kill that cell. There it is right there. I've implemented 2 rules in 1. 0 or 1 means you are exposed. More than 4 means you're overcrowded and you are dead. And notice here, I don't have to check if it's alive, because if it's dead, if it's already dead, well, then I'm going to kill it again and it's fine. And if it's alive, I'm going to go ahead and kill it. So I don't have to worry about that. Now, if the number of living neighbors is exactly 3, then I'm going to revive it. And again, I don't have to, if it's already alive and I make it alive again, it doesn't matter. And so I call the revive function right here. So that's it. And notice the power here. This is really a good example of the power of smart data structures, because I've implemented this in a sort of a clever way, both in terms of how I represent the colony and how I figured out what the living neighbors are. And once I've done that, implementing the rules is trivial. So data and data representation and code really interplay with each other in a very profound way. If you are smart, while I'm talking, let me just go ahead and play this so you can see it one more time, how it unfolds since we've done all this work. If you are smart about how you represent data, then your code is going to be clean and elegant and beautiful. And if you are not, well, then you're going to end up with a mess. And the way you know you've done something wrong with the data is if the code ends up being really messy and gnarly and complicated and hard to explain. And there's an iterative process here. You can't always see what the right data representations are, and you've got to sort of learn from experience. Right now, we don't have a lot of different data structures. We have lists and multi-dimensional lists and a bunch of objects. In 206B, if you're going to join us in a few weeks, we will start to see more and more complex data structures that you can use to decide on what is the best way to represent data so that your code is elegant and simple and efficient. All right, that's it for now, and we'll pick it up next week with some new topics.